The Atomic Bomb, Shaping History and Changing the World. Introduction. The development and use of the atomic bomb during the first half of the 20th century stands as one of the most transformative and controversial chapters in human history. This groundbreaking scientific achievement, born from the brilliance of eminent physicists and shaped by the tumultuous events of World War II, forever altered the course of warfare, international relations, and global security. Key figures like Albert Einstein, James Chadwick, and Otto Hahn played pivotal roles in uncovering the mysteries of atomic physics, while leaders like Harry S. Truman faced the daunting decision of harnessing this extraordinary power. In this narrative, we delve into the discoveries of the neutron, nuclear fission, and special relativity, culminating in the formal establishment of the Manhattan Project and the momentous bombings of Hiroshima and Nagasaki. Together, these events illustrate the profound impact of the atomic bomb, forever marking a threshold between the pre-nuclear and post-nuclear eras, and leaving an indelible legacy that continues to shape our world today. Sir William Crookes, 1832–1919, was a prominent British physicist and chemist known for his work in various scientific fields. Here are some of the key contributions and accomplishments of Sir William Crookes. Cathode rays. Crookes is famous for his investigations into cathode rays, which are streams of electrons emitted from the negative electrode, cathode, in a vacuum tube. His experiments with cathode rays led to the development of cathode ray tubes and laid the foundation for the discovery of electrons. Crookes tube. He invented the Crookes tube, a vacuum tube used to study cathode rays. The tube had a partial vacuum, and when an electric current was passed through it, the cathode rays would be deflected, indicating their particle nature. Crookes radiometer. Crookes is also known for inventing the Crookes radiometer, a device that demonstrates the conversion of light energy into mechanical motion. It consists of a partial vacuum glass bulb with a rotor inside, and when exposed to light, the rotor spins due to the pressure of light on its vanes. Thallium discovery. He discovered the element thallium in 1861 while analyzing the residues from the production of sulfuric acid. Crookes named the element after the bright green spectral lines, thallos in Greek, observed during its identification. Spiritualism and psychical research. Later in his career, Crookes became interested in spiritualism and psychical research. He investigated mediums and claimed to have witnessed paranormal phenomena, which brought him both praise and criticism from the scientific community. President of the Royal Society. In 1898, Crookes became the President of the Royal Society, a prestigious position in the scientific community. Crookes proposes the idea of using atomic energy as a possible source of power. Throughout his lifetime, Sir William Crookes made significant contributions to the advancement of science, especially in the fields of electromagnetism, spectroscopy, and the study of the properties of matter in a vacuum. His work with cathode rays was crucial in the development of modern physics and the understanding of atomic and subatomic particles. Albert Einstein formulated the theory of special relativity in 1905. This revolutionary theory fundamentally transformed our understanding of space, time, and the relationship between matter and energy. The key elements of special relativity are as follows. Invariance of the speed of light. Einstein postulated that the speed of light in a vacuum is constant and is the same for all observers, regardless of their relative motion. This principle contradicted the classical Newtonian mechanics, where velocities add linearly. Time dilation. According to special relativity, time is relative and depends on the relative motion between observers. When an object moves at a significant fraction of the speed of light relative to an observer, time appears to pass more slowly for that moving object as compared to a stationary observer. Length contraction. Special relativity also predicts that objects moving at relativistic speeds will experience a contraction in the direction of motion, making them appear shorter along the direction of travel when observed from a stationary frame. Mass-energy equivalence. Einstein's famous equation, E equals mc superscript 2, states that energy, E, is equal to the mass, m, of an object multiplied by the speed of light, c, squared. This equation shows the equivalence of mass and energy and demonstrates the immense energy contained within matter. Special relativity has been experimentally verified on numerous occasions and has become a fundamental framework in modern physics. It has profound implications for our understanding of the universe, space travel, particle physics, and plays a critical role in various technological applications, such as global positioning systems, GPS, and particle accelerators. James Chadwick, an English physicist, made the groundbreaking discovery of the neutron in 1932. This discovery was of immense significance for the field of nuclear physics and our understanding of nuclear reactions. Here are some key points about James Chadwick's discovery of the neutron. Background: during the early 1930s, researchers were investigating the structure of the atomic nucleus. It was known that the nucleus contains protons, which carry a positive electrical charge, but the total charge of the nucleus was less than the sum of the positive charges of the protons. This led scientists to hypothesize the existence of an unchanged charged particle within the nucleus. Discovery of the neutron. In 1932, James Chadwick conducted a series of experiments at the Cavendish Laboratory in Cambridge, England. He bombarded beryllium with alpha particles, helium nuclei, and observed an unknown radiation that was not deflected by electric or magnetic fields. This radiation could penetrate materials more effectively than expected for alpha particles or gamma rays. Nature of the neutron. Chadwick determined that the unknown radiation was composed of particles with a mass slightly greater than that of protons but with no electric charge. He concluded that these particles were previously unknown subatomic particles, which he named neutrons. Neutrons' role in nuclear reactions. The discovery of neutrons was crucial for understanding nuclear reactions. Neutrons play a pivotal role in inducing nuclear fission, a process in which the nucleus of an atom is split into smaller fragments, releasing a tremendous amount of energy. This discovery was the basis for the development of nuclear reactors and atomic bombs. Recognition and impact. James Chadwick's discovery of the neutron earned him the Nobel Prize in Physics in 1935. His work not only expanded our understanding of atomic and nuclear physics but also had significant implications for nuclear technology and energy. The discovery of the neutron was a monumental achievement that opened up new avenues of research in nuclear physics and ultimately paved the way for significant advancements in both peaceful and military applications of nuclear energy. Otto Hahn and Fritz Strassmann, both German physicists, made the pivotal discovery of nuclear fission in 1938. Their groundbreaking experiments demonstrated that bombarding uranium with neutrons could indeed split the uranium nucleus into smaller fragments and release a substantial amount of energy. Here are the key points about Hahn and Strassmann's discovery of nuclear fission. Background: in the 1930s, physicists were investigating the properties of atomic nuclei and conducting experiments to explore the effects of bombarding them with various particles, particularly neutrons. Uranium experiments. In late 1938, Otto Hahn, along with his assistant Fritz Strassmann, performed experiments in Berlin, Germany. They bombarded uranium nuclei with slow-moving neutrons, a process called neutron irradiation, in an attempt to study the effects of neutron capture by uranium. Unexpected results. Hahn and Strassmann were surprised by the results of their experiments. They found that the uranium nucleus, after capturing a neutron, would split into two smaller nuclei, along with the release of several additional neutrons. Nuclear fission. Hahn and Strassmann had inadvertently discovered nuclear fission, the process of splitting an atomic nucleus into smaller fragments. This process released a tremendous amount of energy and additional neutrons, which could, in turn, cause more uranium nuclei to undergo fission in a chain reaction. Theoretical explanation. Subsequently, the physicists Lisa Meitner and Otto Frisch provided a theoretical explanation for the phenomenon of nuclear fission. They correctly interpreted the experimental results and proposed that the uranium nucleus, after capturing a neutron, became highly unstable and split into two roughly equal-sized fragments. Significance. The discovery of nuclear fission was a milestone in nuclear physics and had far-reaching consequences. It laid the foundation for the development of nuclear reactors, which harness controlled nuclear fission to produce electricity, and atomic bombs, which exploit uncontrolled nuclear fission for devastating energy release. It's worth noting that Otto Hahn was awarded the Nobel Prize in Chemistry in 1944 for his work on nuclear fission, but Fritz Strassmann was not included in the Nobel Prize. However, both scientists' contributions to the discovery of nuclear fission were of immense importance and have shaped the course of modern physics and technology. In August 1939, Albert Einstein signed a letter to President Franklin D. Roosevelt, which played a crucial role in alerting the United States government about the potential development of atomic weapons by Nazi Germany. This letter ultimately led to the establishment of the Manhattan Project, a top-secret research and development program that aimed to build the first atomic bomb. Here are the key details about the letter. Background. As a result of the rise of Nazi Germany and the outbreak of World War II, there were concerns among some scientists that German scientists might be working on developing atomic weapons. The letter, dated August 2, 1939, was written by physicist Leo Szilard, but it was co-signed by Albert Einstein. Szilard was a Hungarian physicist who had fled Europe due to the political situation and sought refuge in the United States. The letter was addressed to President Franklin D. Roosevelt and delivered to him through personal channels. Content. The letter outlined the potential military applications of nuclear fission, particularly the possibility of creating extremely powerful bombs that could have devastating consequences. It warned that if Germany succeeded in developing such weapons, it could pose a serious threat to world security and the United States. The letter urged the U.S. government to initiate its own research into nuclear fission and atomic energy to ensure that the United States remained at the forefront of this field and prevent potential adversaries from gaining a significant advantage. Impact. President Roosevelt was convinced of the importance of the letter's message and recognized the urgency of investigating atomic energy. As a result, the U.S. government established the Advisory Committee on Uranium, which marked the beginning of the American efforts to build an atomic bomb. This eventually led to the formation of the Manhattan Project in 1942, a massive research and development program that brought together some of the world's leading scientists to work on developing the atomic bomb. Albert Einstein's signature on this letter helped draw attention to the potential military significance of nuclear fission and played a significant role in initiating the American atomic weapons program, which would later lead to the development and use of the atomic bomb during World War II. The United States formally established the Manhattan Project in 1942. The Manhattan Project was a highly classified research and development program aimed at building the world's first atomic bomb during World War II. The project's name was derived from the location of its main headquarters, which was situated in Manhattan, New York. Key points about the Manhattan Project. Origins. The origins of the Manhattan Project can be traced back to the letter sent by physicist Leo Szilard and co-signed by Albert Einstein to President Franklin D. Roosevelt in August 1939, warning about the potential military applications of nuclear fission. Formation. In response to the concerns raised in the letter, the U.S. government established the Advisory Committee on Uranium in 1939 to investigate the feasibility of atomic weapons. This committee later evolved into the Office of Scientific Research and Development, OSRD, in 1941, under the leadership of Vannevar Bush. Under Army control, the responsibility for the project was transferred to the U.S. Army in 1942, with General Leslie R. Groves appointed as the military leader in charge of the effort. The project was given the code name Manhattan Engineer District, or simply the Manhattan Project. Key sites. The Manhattan Project involved several research and production facilities across the United States, each specializing in different aspects of atomic bomb development. The main research and design centers were located in Los Alamos, New Mexico, where theoretical work and bomb design took place, and in Oak Ridge, Tennessee, where uranium enrichment was carried out. Contributions of scientists. The project brought together some of the world's most brilliant scientists, including Robert Oppenheimer, Enrico Fermi, Richard Feynman, and others, who worked on various aspects of the bomb's design and development. Trinity test and bombing of Hiroshima and Nagasaki. The Manhattan Project culminated in the successful test of the first atomic bomb, codenamed Trinity, on July 16, 1945, in the New Mexico desert. Subsequently, atomic bombs were dropped on the Japanese cities of Hiroshima, on August 6, 1945, and Nagasaki, on August 9, 1945, during the final stages of World War II. The Manhattan Project was a massive and highly secretive undertaking, involving the collaboration of thousands of people from diverse scientific, engineering, and military backgrounds. Its successful culmination with the development and use of the atomic bomb had a profound impact on world history and ushered in the nuclear age. Harry S. Truman, the 33rd President of the United States, played a significant role in the decision to use the atomic bomb during World War II. Truman assumed the presidency on April 12, 1945, following the death of President Franklin D. Roosevelt. Key points about Harry S. Truman and the atomic bomb. The Manhattan Project. When Truman became president, he was informed about the top-secret Manhattan Project, which was developing the atomic bomb. He was previously unaware of the project's existence and the progress made in its development. Potsdam Conference. In July 1945, Truman attended the Potsdam Conference in Germany, where he met with British Prime Minister Winston Churchill, later replaced by Clement Attlee, and Soviet Premier Joseph Stalin to discuss post-war Europe and the war against Japan. Successful Trinity Test. While the conference was ongoing, the successful test of the first atomic bomb, Trinity Test, was conducted on July 16, 1945, in New Mexico. The test demonstrated the bomb's immense destructive power. Decision to use the atomic bomb. By the time of the Potsdam Conference, Japan was already on the verge of defeat, but its leaders had not yet surrendered. Truman was faced with the difficult decision of whether to use the atomic bomb as a means to end the war quickly and avoid an invasion of Japan, which would likely result in significant casualties on both sides. Hiroshima and Nagasaki. On August 6, 1945, Truman ordered the dropping of an atomic bomb, codenamed Little Boy, on the Japanese city of Hiroshima. The bomb caused immense destruction and loss of life. When Japan did not surrender, a second atomic bomb, codenamed Fat Man, was dropped on Nagasaki on August 9, 1945. Surrender of Japan. The devastating impact of the atomic bombings and the Soviet Union's declaration of war against Japan on August 8, 1945, led to Japan's unconditional surrender on August 15, 1945, effectively ending World War II. Truman's decision to use the atomic bomb has been the subject of ongoing debate and controversy. Supporters argue that it hastened the end of the war and saved lives by preventing a prolonged and bloody invasion of Japan. Critics contend that the use of such a devastating weapon on civilian populations was unnecessary and morally questionable. Regardless, the atomic bombings of Hiroshima and Nagasaki marked a turning point in history and ushered in the nuclear age with profound implications for international relations and warfare. August 6, 1945, was the date when the United States dropped an atomic bomb on the Japanese city of Hiroshima. The bombing was carried out by the American B-29 bomber, called the Enola Gay, and the atomic bomb was codenamed Little Boy. The explosion destroyed most of the city and killed approximately 70,000 people instantly, with tens of thousands more dying from injuries and radiation exposure in the following weeks and months. The bombing of Hiroshima was a major turning point in World War II, as it led to Japan's surrender and the end of the war. However, the use of atomic bombs remains controversial, and many people have criticized the decision to use them, citing the devastating effects on civilian populations and the potential for nuclear warfare to cause global devastation. August 9, 1945, was the date when the United States dropped a second atomic bomb on the Japanese city of Nagasaki. The bombing was carried out by the American B-29 bomber, called Boxcar, and the atomic bomb was codenamed Fat Man. The explosion destroyed much of the city and killed approximately 40,000 people instantly, with thousands more dying from injuries and radiation exposure in the following weeks and months. The bombing of Nagasaki came just days after the bombing of Hiroshima and was another major factor in Japan's decision to surrender, which led to the end of World War II. Like the bombing of Hiroshima, the use of atomic bombs on Nagasaki remains controversial, with some arguing that it was unnecessary and others asserting that it was a necessary measure to bring an end to the war quickly and save lives that would have been lost in an invasion of Japan.